Hi, my name is Harish Raj and my matrix number is 241110919. Today we will discuss the Reynolds transport theorem, or RTT, a fundamental concept in fluid mechanics. RTT bridges the gap between system analysis and control volume analysis, which is essential for studying dynamic systems like fluid flows. It provides a mathematical framework to analyze the conservation of mass, momentum, and energy for a given control volume. There's two methods of analyzing the spraying of deodorant from a spray can. A. We follow the fluid as it moves and deforms. This is the system approach. No mass crosses the boundary and the total mass of the system remains fixed. B. We consider a fixed interior volume of the can. This is the control volume approach. Mass crosses the boundary. The relationship between the time rates of change of an extensive property for a system and for control volume is expressed by RTT. Why is RTT important? In real-world problems, we often deal with open systems where mass, energy, and momentum cross boundaries. RTT also helps convert the system approach, fixed mass, into the control volume approach, fixed region in space. This is crucial in engineering applications like designing turbines, analyzing pipelines, and modeling aerodynamics. The time rate of change of the property B of the system is equal to the time of rate of change of B of the control volume plus the net flux B out of the control volume by mass crossing the control surface. dB system over dt equals to dBCV over dt minus B inlet plus B outlet. This equation applies at any instant in time where it is assumed that one system and the control volume occupy the same space at that particular instant in time. A moving system hatched region and a fixed control volume shaded region in a diverging portion of the flow field at times t and t plus change in time. The upper and lower bound are streamlines of the flow. Let B represent any extensive property. Before that, let me explain what is extensive property. Extensive properties depend on the amount of matter. Examples: mass, momentum, energy. The symbol is B. On the other hand, intensive properties, independent of the amount of matter, for example pressure, temperature, and velocity. Let B represent any extensive property such as mass, energy, or momentum, and let B over M represent the corresponding intensive property. Nothing that extensive property are additive. The extensive property B of the system at times t plus t different times is expressed as B system t equals to BCVT. The integral of BPV times NdA over the control surface gives the net amount of property B flowing out of the control volume into the control volume if it is negative per unit time. RTT fixed CV. dB system over dt equals to d over dt. Rho B dV plus PBV times NdA. Alternative RTT fixed CV. dB system over dt equals to rho over rho t PB dV plus PBV times NdA. Relative velocity VR equals to V minus VCS. RTT non-fixed CV dB system over dt equals to dB system over dt equals to d over dt PBTV plus PBVR times NDA. RTT steady flow dB system over dt equals to PBVR times NDA. Relative velocity crossing a surface is found by vector addition of the absolute velocity of the fluid and the negative of the local velocity of the control surface. An example control volume in which there is one well-defined inlet 1 and two well-defined outlets 2 and 3. In such cases, the control surface integral in RTT can be more conveniently written in the terms of the average values of the fluid properties crossing each inlet and outlet. In conclusion, Reynolds transport theorem connects system-based and control volume-based analysis, making it invaluable for studying dynamic systems. By incorporating both extensive and intensive properties, RTT helps us understand the behavior of mass, momentum, and energy in fluid mechanics. Whether it's pipeline, engines, or environmental flows, RTT is a key tool for engineers to analyze and optimize real-world systems. Thank you.